Welcome back, everyone. This is ARC4CFD, Section 1, Lecture 5. I cannot believe this is the last lecture of Section 1, so congratulations, you have made it through. But this is actually a pretty important lecture because it will take you through a complete real-life example of how to run numerical simulation on the HPC system using everything you have learned in previous sections. Okay, so let's dive into it. Again, the goals are to follow the workflow of a numerical simulation on an HPC system, starting with the discretization of the governing equation, define the initial and boundary condition of the problem, implement a distributed memory parallelization strategy for to solve your problem in the most efficient way, and describe the typical workflow in HPC computation. Okay, so the first thing is, what problem are we trying to solve? In this case, what we present is a very simple 2D heat conduction problem where we want to study how the heat distributes, the temperature distributes inside this rectangular plate, given some boundary condition and given the heat source at the center. Um, so we all know that this is a problem described by the very well-known Poisson equation, equation 1, which is a PDE, is a partial differential equation of elliptic type. Q dot right there is the source, the heat source, and K is the thermal conductivity of the material, and T XY is the temperature field inside the plate. Now, when you write this in components and you decompose the Laplacian operator, it becomes equation 2, which is the one that we need to basically solve. And so to solve an equation, and this will be no different if you're solving Navier-Stokes equation for fluid flows, you need to follow a 4 steps process to the numerical solution, where step 1 is basically the discretization of the spatial domain. Step 2 is the transformation of the partial differential equation to algebraic equations, equations that can be solved using a computer, and definition and application of boundary condition, and finally solve the algebraic equation until convergence. And we will see very soon what this actually means. So the first step, discretize the spatial domain. Basically, what you do is you stop thinking about the plate as an homogeneous material and continuous material, but you divide it in several grid points. And again, the choice of the number of grid points is dependent on the amount of computational resources you have available. But basically, in this schematic, you divide it in a finite number of grid points. The moment you divide in a Cartesian grid like this, you can map every point with a couple of indices I, j. And delta x and delta y here are the grid spacing in x and y. So this is step 1. We forget about the figure on the left and we only consider the grid that we have on the right. After that, you need to transform the partial differential equation that I showed you before, equation 2, into algebraic equation. This step is done by choosing discretization or method in this case. So what you can do is you can go in the literature. We are using in this example the finite difference method, but there are many other methods that you can use: finite volume methods, finite element methods. These are all methods that will take your equations PDE and will transform them in equations that are solvable using your computer or HPC system. At that point, you want to define the boundary condition. The problem is not closed until both the initial and boundary condition are defined. So in this case, we know what is the temperature on all sides of this plate, and so we apply that in the grid points that are sitting on the boundary. And finally, we select the solution methods. So again, we have a couple of options. We can use direct methods and iterative methods. And in this specific example, which is also very common in computational fluid dynamics, we are going to use iterative methods. And one thing that is important to realize is that the moment you choose to solve your problem numerically, you give up um, reaching the exact solution. You will never reach the exact solution, but you will reach an approximate solution. And how good this approximate solution is based on or depends on all the choices that you made step 1 to 4. So the choice of the grid, the choice of the discretization method, the choice of the solution method, and so on. So in this case, we need to answer the question, when do we stop iterating? And that is basically the convergence method, which will be described in this lecture. And finally, we will also quickly take you to a quick visualization of the result, because at the end of the day, after your computation is done, what you want to do most likely is to analyze your data and visualize that everything makes sense. So once again, I highlight I acknowledge the collaboration between MPI Lab, Computer Ontario, and University of Waterloo for this course. I thank you so much, and I will see you in the next section.